Hi, this is Jerry Pinter. Welcome to part 4 of our lecture on chapter 2. In this part of the video, we'll be doing continuous time LTI systems and linear differential equations. In this video, I'm going to introduce differential equations and how to solve them. This material will be much easier to handle if you've already taken a math course on differential equations or a mathematical methods type of class. If you haven't had such a class, I'll show you the basics in this video. However, we're going to cover the material very quickly, so you may need to learn some of these concepts on your own and at your own pace outside of class. After all, this is a signals and systems class, not a math class. So let's get started. We're going to begin with looking at how continuous time LTI systems can be described by linear differential equations. Let's start with an example. Suppose we have a spring here with a mass on the end of it, and this mass is allowed to slide back and forth on the table here, and we're going to assume that there's no friction. However, we are going to include wind resistance. So you've seen problems like this in your physics classes, either in basic physics, or maybe you've taken a mechanics type course that looked at this problem in a little more detail. But this is a good place for us to start because you're already familiar with the basic physics of the system. But our goal here is to describe this system using an equation of motion that describes the position of this mass here as a function of time. And it turns out that this is going to be a linear differential equation. And so kind of the main idea here is that many continuous time systems can be described by linear differential equations. So they're an important, very important class of equations in mathematics and physics. So the system, you can see initially here, this is at time 0. The mass is over here at position A. Position 0 here, that's the equilibrium position where the spring is relaxed. So at time 0, we release the spring. It's stretched right now, and you can kind of remember from physics class what's going to happen is this mass is going to oscillate back and forth with amplitude given by A. So we're going to model the spring force, of course, with Hooke's law. The force is equal to minus kx, where k is the spring constant. And we're going to include wind resistance, so we're going to model drag or wind resistance using Stokes' formula, which again you might remember from your physics or mechanics class. The wind resistance force is given by the opposite of B times V, where B is a constant or coefficient. It's a drag coefficient. And V, of course, is the velocity or the speed. So how do we do this? Well, it's pretty straightforward. We're going to use Newton's second law. Net force equals mass times acceleration. And to think about the net force, what are the forces acting on this spring? We're talking about in the horizontal direction, of course, because in the vertical direction, weight and normal force cancel out anyway. So in the horizontal directions, there are two forces acting on this mass. There's the spring force, which remember by Hooke's law is minus kx. And there is the drag force, which by Stokes' formula is minus BV. So we add these two, negative forces here together to get the net force, and that's equal to ma, mass times acceleration. So we want to put everything here in terms of x, the position of the mass. Notice this is the x-axis up here. So the first term already is in terms of x, so we have minus kx. The second term, we have velocity, but velocity, of course, is the derivative of the position. So we can replace v here with dx dt. And then acceleration over here on the right side is the second derivative of position. So we have d squared x over dt squared, the second derivative of x. So what we can do here is it's customary to just sort of rearrange all these terms here and put the highest order derivative over here on the left. So let's put this term over here, right here, and we'll bring this term to the other side. So we get m times the second derivative of x plus b times dx dt plus kx equals 0. So this is a differential equation. And a differential equation basically means it's an equation that has derivatives of the variable that we're trying to solve for. Okay, so we can't solve this obviously using algebra. It's not an algebraic equation, it's a differential equation. And this equation basically describes the motion, or it's the equation of motion or equation of position for this mass right here. Now, obviously, having the equation is great, but we're going to want to solve it. And the details of that is basically going to be explained throughout this video of how we do something like this. And we'll actually solve this equation much later in the video here. By the way, just to get a sense of, what is the solution to this, I show the solution here. The solution, it turns out, has two parts to it. There's an oscillating part here represented by a cosine function. And that makes sense because remember, this mass is going to oscillate back and forth with some frequency omega. And so you can see these oscillations here. But because there's friction, or I should say damping, due to the drag or the wind resistance, we have this term out in front. There is a decaying exponential function. And as time grows, this e to the minus sigma t gets smaller and smaller. So what happens is these oscillations get smaller in amplitude with time, and eventually they die out, and the mass here comes to rest at the equilibrium position. So we'll see how to solve this equation here, and we'll get this solution. That's our sort of one of our ultimate goals in this video, is to get to where we can solve this. Here's a little bit more complicated application of that problem we just looked at. This is how to model an automobile suspension system. So on your car, you have, this is representing the car here, the chassis of the car, which has, some large mass. And your suspension system consists of basically a spring and a shock absorber. Okay, and these two things work together to give you a nice smooth ride when you're going over bumps. So what we're going to do here, and we're not going to go into this in super great detail, but it's just a kind of to show another example of how a mechanical system can be represented by a differential equation. So in this case, our system here, our automobile suspension system, or basically the car, is our system, and the input to this system is basically going to be the road, or that is the tire, how it goes over the road. And the output of this system is going to be how the car responds. So, basically it's a spring, with it's a damped spring, just like in the last problem, but it's a little more complicated because now we have something that's driving the spring. That is the road down here, the surface of the road, which we call X, is pushing the tire up and down, as you go over bumps, and then the spring and the shock absorber work to, smooth out those bumps, and then the car up here is going to respond. So the output of the car is Y. That's the height of where the car is. Where the tire is X. So that's why we now have an input and an output. But again, the math to figure out the differential equation, it's somewhat similar to the last problem. We're going to use Newton's second law, net force equals ma. And this time we've got three forces acting on the car. There's the spring force, which by Hooke's law is going to be minus k. Now the difference here is instead of just x, it's y minus x, because the spring sees its what's key is here is the displacement of the spring. So that means the upper position of the spring, y, minus the lower position of the spring, which is given by x. That's the displacement. So that's why we have minus k times y minus x. Likewise, the drag force, that's this shock absorber force here. All right, it's modeled as a drag force given by that Stokes formula that we saw in the last slide, which is b, some coefficient, and here instead of just velocity, it's the difference in the velocity of the top and the bottom. So we have the Vx minus Vy to do the drag force here, because if they're both moving at the same velocity, then there's no drag force. But it's when they're moving at different speeds, the top and the bottom of the shock absorber, that's when there's some drag force there. And then I've got gravity in here also, which is just a constant mg force here pointing down. And then on the right side, just like before, we have the mass times the second derivative of position. In this case, it's d squared y dt squared because we're using y as the position of the car chassis up here. So, the next thing to do here is these velocities here, vx and vy, are expressed as the derivatives of position. So the x velocity is dx dt, the y velocity is dy dt. And so finally, we can sort of rewrite all this stuff, and it's customary to put all the output variables on the left. So that's the y that we're going to want to solve for. So we have mass times second derivative of y plus b times first derivative of y plus k y, and then all the x's and anything else are on the right. So we have b times dx dt plus k times x minus mg. So this is, a rather complicated differential equation, and we'll learn, this is called a second order linear differential equation because it has a second derivative as the highest derivative. And we're not going to actually solve this one in this lecture, but the key thing that I wanted to show you here is that we can model, a fairly complex system like an automobile suspension system. We can model it using a differential equation. One of the other important applications of using differential equations is for solving electrical circuits, in particular circuits that contain either capacitors or inductors. So in general, an RLC circuit has a resistance, an inductance, L, and a capacitance, C. And the way to solve these types of circuits is by finding a differential equation that describes the circuit. So how do you do this? Well, it's actually not that bad. For each of these components, R, L, and C, there's an equation for its voltage and likewise for its current. So for example, the resistor is the easy one. The voltage of a resistor is just by Ohm's law, V is equal to IR. And likewise, we can solve for current. The current through a resistor is equal to its voltage across the resistor divided by the resistance. Okay, so this is, the easy case. For an inductance, you'll remember again from your physics or electronics class that the voltage across an inductor is given by L, the inductance, times di dt. This is the time derivative of the current. All right, this is the rate of change of current. Now we can solve for I in this equation by moving the dt to the other side and integrating, and the current through an inductor is 1 over L times the integral of V dt. So these two equations are actually the same equation. It's just that this one is solving for V and this one is solving for I. What about the capacitor? Well, capacitor, you probably remember again, from your physics or electronics class, that the current I through a capacitor is equal to C times dV dt, where dV dt here is the rate of change of the voltage across the capacitor. And we can solve this equation for V by basically integrating it. And so the voltage across the capacitor is equal to 1 over C times the integral of I dt. So with this table here, basically given an RLC circuit, you can use Kirchhoff's voltage loop law as needed, which basically says that all the voltages, going around a loop have to zero out. You can also use Kirchhoff's current law, or current continuity as it's sometimes called, as needed. In other words, current is conserved. Whatever flows into a junction has to flow out. And so these are just basic circuit rules that you learned in, again, your physics or electronics class. Finally, once you do that, you can write all the voltages in terms of the output and the input voltage. And if you end up with some integrals like these two right here in the equation, you can always take the derivative of the equation to get rid of those integrals. So we'll look at a couple examples of how to do this next. So here's an example of an RLC circuit, and we're actually going to look at a couple different methods of how to come up with the differential equation. But we're given this circuit shown right here. You can see the resistance, the inductance, and the capacitance here. And the input voltage is over here on the left. So that's going, you can think of this circuit basically inside this box as a system, and it is. It's an LTI system. So the input to our system, which we usually call X, is actually the input voltage over here. And we're going to take the voltage right here as the output of this circuit. So that is going to be the output of our system here. And our goal here is at this point, we're not going to actually solve for the output, but we just want to come up with a differential equation that describes this circuit here as a system. So to do this, and again, I'm going to go through these steps rather quickly because I assume that this should be some review for you guys because you've seen stuff like this before in your other classes. But the voltage loop equation, starting over here with the input voltage, this voltage here has to be equal to the voltage across R, L, and C all added together. So I have VI equals VR plus VL plus VC. And notice that the voltage on the capacitor is the same as the output voltage. So let's replace VC with V out right here. Now, from the table on the previous slide, we know that VR, the voltage across the resistor, is equal to IR, that's Ohm's law. We know that the voltage across the inductor is given by L times di dt. And the other thing, which we're going to actually use here, is that the current through the capacitor is equal to C times dV dt, where the capacitance voltage, remember, is this output voltage here. So the first thing we can do is take this expression here and substitute it in for VR. We'll take this expression and substitute it in for VL, and we get this equation here. The input voltage, VI, is equal to IR plus L di dt plus the output voltage, V out. Now, the next thing we can do here is we can replace, there's an I here, and there's an I here. Let's replace that I with this expression here, where I is equal to C times dV out dt. So right here, you can see this I just replaced the I with this. And then this I, you have to, of course, take the derivative of it. So the derivative of this here is just C times the second derivative of output voltage. So that's been substituted in right here, and then we'll leave this last term as just V out. So what we have now is this, in step 4 here, this equation is an equation that expresses the output voltage in terms of the input voltage. It's customary to usually rewrite this a little bit. You wouldn't have to, but let's move the, again, the highest order derivatives over on the left. So here's our second derivative, here's our first derivative, and here's just V out by itself. The other thing, what we can do here to clean it up a little bit, we can divide every term by LC. All right, now why would we do that? Well, one reason is that, remember that 1 over LC is the square of the natural frequency, right? The natural frequency of any circuit that has inductance and capacitance is equal to the square root of 1 over LC. So this just, cleans up these terms a little bit. We can write these terms in terms of the natural frequency. So we end up with second derivative of the output voltage plus R over L times the first derivative of the output voltage plus omega naught squared times the output voltage is equal to omega naught squared times the input voltage. So notice we put all the VOs on the left, all right? Those are our outputs, and we put all the VIs, there's just this one term, on the right. That is our input. So here is our equation that describes this circuit up here, and if we wanted to and we know how to, we would next solve this equation, but we're not quite there yet. This is basically the same example that we just did. It's just a slightly different method to arrive at the same result. So I'm not going to go through this in great detail here, but basically, you're starting out with the same circuit. You write the voltage loop equation. Everything's the same here. The only difference is for the output or the capacitance voltage over here, from the table we're going to use, if you look back a couple slides, it's 1 over C times the integral of I dt. And So, now we can use the capacitor current relation. Again, I is equal to C dVO dt, and therefore the derivative, which is shown right here, is given by this right here. So now we can substitute these values into this equation here. And when, kind of when the dust all settles here, you can go through my steps if you want to see the details of what I did here. But for example, this 1 over C cancels that C here, and this dt and this dt cancel, leaving just the integral of dV out, and that's just equal to V out. So, everything comes out to be the same, and we end up with the same a differential equation. So as you can see, there's more than one way to skin a cat, as they say. There's a couple of different methods to get the same differential equation. And just for completeness, I'm going to even show you a third method to find the same differential equation for this same circuit. This one is a little more fundamental, I guess, in a sense, because it uses current. So you write, again, we write the voltage loop equation, just start like we did before. We, find the voltage expressions for VR, that's Ohm's law, V equals IR. For the inductor, V equals L times di dt, and the current through the capacitor is C times the derivative of the voltage across the capacitor. Now, what's different about this approach is that, remember that I, which is current, is how much, it's basically the rate of flow of charge through the circuit. So we can replace I with dq dt. Okay, that's the time derivative of the amount of charge. And so over here where we had di dt, well, that's going to be the second derivative of q. All right, and then in this equation here, we have, on the left, we have I, which is dq dt, and then over here we have the dv dt, which stays the same. And by the way, this can be solved. What you can do here is basically integrate both sides of this equation, and you come up with an equation you might remember from physics or electrostatics. The charge on a capacitor is equal to C times V, the capacitance times the voltage across the capacitor. So, Q equals CV comes from this, you can see it can actually be derived from this current formula up here. So the voltage on the capacitor is Q over C. All right, so with all these things, we can rewrite our initial equation up here using these results that I have in the boxes here. So by making those substitutions, you end up with this equation. And notice this is an equation, at least on the right side, in terms of Q. So finally, you can express everything in terms of the output voltage, because VC is actually equal to V out. And again, when everything settles out here, we end up with the same equation that we had on the other slide. So this is, just a third method or approach to solving this type of equation using charge instead of current and voltage. A slightly different approach to this type of problem is maybe instead of wanting to find the voltage, we wanted to find a differential equation that describes the current going through this equation. All right, so in this case, our system here is still the same circuit, but now we're going to think about this system as having a voltage input, which is over here, and where our output of this system is going to be the current that flows through it. So, our analysis is somewhat similar. We can start with a loop equation here. We can put those expressions for voltages into this loop equation up here to get this result here. And the nice thing about this result is you can see we have current and current and current. So everything on the right side is current, which is our output variable that we're trying to solve for. Now, because this is a kind of a weird equation because it's got a derivative and it's also got an integral. So it's a differential and integral equation. So the way to fix that is just to take the derivative of the whole equation to get rid of this integral right here. So you can see if we take the derivative term by term, on the left side we get dvi dt. Here we get di dt times r. And here we get L times the second derivative of current. And then when we take the derivative of the integral here, this integral just, gives us back I, all right? The derivative basically undoes the integral. So we get 1 over c times I. And now we can, rewrite this thing with all the i's on the left, because remember the I, that's our output of this system. So we're going to put all our outputs on the left, and then here is our input, which is, remember, our input is over here. It's the voltage here. And you can see when we're doing current, the input, we're actually going to be taking the derivative of the input voltage over here. But so this is a different differential equation, obviously, than what we got before, because this differential equation describes the current going through this circuit as a function of time. And of course, we would have to solve this equation. And like I keep saying, we don't know how to solve these yet, right? Well, we're going to get to that shortly. So in the last section, we saw how we can take a physical system like a spring with a mass, or an automobile suspension system, or an LCR circuit, and we can describe that system using a differential equation. But really the most important thing, of course, is to solve that differential equation, because that's going to give us the solution to the problem that we're looking for. So that's what we're going to do now, is we're going to learn how to solve these differential equations, and we're going to start with a type of differential equation called a homogeneous differential equation, which is the simplest type to solve. And I should also mention that in your lecture notes, there is an appendix with more examples if you need to see a little bit more of this than what I'm covering during this lecture. So let's start with our methods of how to solve these things. So we're going to start out by learning how to solve homogeneous linear differential equations. So that's quite a mouthful. Let's see what we mean. Let's break this apart and see what we mean by this. So first of all, the order of the differential equation basically tells us what the highest derivative is. So in other words, a first order differential equation contains a first derivative as the highest derivative. A second order contains a second derivative, and it probably contains a first derivative as well. A linear differential equation, which is what we're dealing with in this class, is when the coefficients are constants and they do not contain any of the variables like x, y, or t. And finally, this word homogeneous just means that the right side of the differential equation is 0. And what this really means is that there's no forcing function or source function to the differential equation. So let's look at some examples here before we even start to think about how to solve this. So here's an example of a first order homogeneous linear differential equation. df dt plus 3f equals 0. Now f is a function of time, okay? So notice on the right side, it's 0, all right? That means it's homogeneous. And here are, let's see, our derivatives here. This is our highest derivative, is just a first derivative. That's why it's called first order. What else? Well, the coefficients, there's a 1 in front of here, and there's a 3 here. Notice that these are linear coefficients. They're just constants, all right? We don't have an x or a y or an f or t or anything like that in front of the functions here and the derivatives. Now, this is another one. A times dy dx plus b times y of x equals 0. So again, we see, these are constant coefficients, which make it linear. This is a first order derivative, so it's a first order equation. And the right side is 0, so it's homogeneous. Down here are some examples of second order linear differential equations that are homogeneous. So notice in both these examples here, we see a second derivative, all right, that is the highest derivative. But there's also a first derivative, okay? And but this makes it a second order equation because of that second derivative. So, it's pretty basic terminology there. These are both linear because notice all the coefficients are just constants. And these are both homogeneous because the right side of these equations is 0. So let's take a look at an example and see how to solve this. So we're told that a quantity y varies with time according to the equation below. And the initial value of y at t equals 0 is 100. Determine y as a function of time. So the equation that we're given is dy dt equals minus 5y. Okay, and our goal, of course, is to solve for y. So let's rewrite our differential equation. Let's put all the y's over on the left side. So we have dy dt plus 5y equals 0. Now, what we do here, and again, I'm not going to prove this, but this is something you learn in your math class, is that solutions to these type of equations are exponential functions. Okay, so the idea here is that exponential functions solve linear differential equations. So we're going to assume that the solution has an exponential form. So in other words, y is equal to some constant a times e to the st. Okay, so t obviously is our time variable here. We don't know what a is and we don't know what s is, all right, but we're going to figure that out. So the way to do this is kind of the long way, and I'm going to show you a shorter way shortly on how to do this. But for now, if we think about substituting this, our kind of like our trial solution back into our equation up here, we get s times a times e to the st plus 5a e to the st equals 0. Now, how did I get that? Well, notice I have to take the derivative of y here. So when you take the derivative, here's y, a e to the st. When I take the derivative, remember that s comes out to the front. Okay, that's just regular calculus there. So, and then, here I have 5 times y, so that's why I have 5 times a e to the st. All right, now notice when we do this, both terms have e to the st. So we can cancel that out. All right, now later on I'm going to show you how to do this without even writing the e to the st, but for now let's just put it in there, and we notice that it cancels. So what we end up with up here, and also notice the a cancels out, right? They both have an a in it. So we can divide, left and right side, everything by a times e to the st, and what results is a very simple equation. It's s plus 5 equals 0. This is called the characteristic equation of this differential equation right here, okay? So s plus 5 equals 0, that's easy to solve for. S is equal to minus 5. So minus 5, we say, is the root of the characteristic equation for this differential equation. And then we can substitute the minus 5, S is minus 5. Let's put it back into our trial solution up here. So my solution now is y is equal to a times e to the minus 5t. The next thing is all we have to do now to finish the problem is figure out what a is. But a can easily be figured out by using the initial condition that was given to us up on the problem. When we evaluate y at 0, we're supposed to get 100, right? That was given to us. So 100 is equal to a times e to the minus 5 times 0. Well, that's just e to the 0, which is, of course, 1. So therefore, we have just shown that a is equal to 100. So our final solution is y of t is equal to 100 times e to the minus 5t. So this is the solution that basically satisfies or solves this system described by this differential equation up here. Now there's a couple steps in what we just did that we can shorten considerably and make the whole process much more efficient. We can write the characteristic equation actually just by inspection, by looking at the differential equation. And this is a really nifty trick that saves us a lot of time. So notice, this is the last problem that we just did. We had, dy dt plus 5y equals 0, and we plugged, we substituted that y equals a to the e to the st into this equation, and we got this result here. And then when we divided by a times e to the st, basically dividing by y, we got this, s plus 5 equals 0. So the way to do this by inspection with a shortcut is that whenever we see a first derivative, that gives us an s. Whenever we see a y like this, we don't write, it just kind of returns a 1. So it just returns the coefficient. So by looking at this equation right here, I can see that I have an s here, and all I have here is a 5. So it's s plus 5 equals 0. Now, what about if there's a second derivative? Well, if there's a second derivative here, we get s squared. And, if there were a third derivative, we would get s cubed, and so on. So that brings us to second order differential equations. Now, the difference here is that second order differential equations have two roots of their characteristic equations. So we'll call those roots S1 and S2 to distinguish the two roots from each other. And the solution has the form of y of t is equal to a1 times e to the s1t plus a2 times e to the s2t. So this is sort of a superposition of the two solutions, one solution for each root here. So just to show an example here, let's say we're given this differential equation. The second derivative of y plus 2 times the derivative of y minus 8y equals 0. And we're given these two initial conditions here, y of 0 equals 0, and the first derivative of y at time 0 is equal to 18. So here is our differential equation again. I just rewrote it. Let's write the characteristic equation by inspection. So look at how easy this is. This second derivative just gives me an s squared. This is 2 times the first derivative. That gives me a 2s. And then we have minus 8y. That just gives me minus 8. And of course, that's equal to 0. So this is the characteristic equation, s squared plus 2s minus 8 equals 0. We have to solve this equation, which is simple. We just factor it. So we have s plus 4 times s minus 2 equals 0. So the two roots to this characteristic equation are s equals minus 4 and s equal positive 2. So my solution of this problem has the form a1 times e to the minus 4t, notice minus 4 is that root there, plus a2 times e to the 2t, where 2 is the second root right there. Now, we have to figure out what these two coefficients are, a1 and a2. Well, we've got two initial conditions that will allow us to do that. So the first initial condition says that y at time 0 is equal to 0. We were given that, let's see, right here, okay? And therefore, 0 is equal to a1 plus a2. All right, I'm getting that by plugging in 0 here. And therefore, a1 is equal to minus a2. So we don't know what a1 is yet, but we know it's opposite of a2. So I can make a substitution, and I can plug in, for a1, for example, I could plug in negative a2, or for a2, I can plug in negative a1. The second the second initial condition is y prime at time 0 is equal to 18. So again, figuring out y prime and plugging in t equals 0, you end up with this expression here, negative 4a1 plus 2a2 has to equal 18. So what we've got here are two equations and two unknowns. You know how to solve for that. That's just basic algebra. You can do it by substitution. And you'll end up with a1 is negative 3 and a2 is equal to positive 3. So plugging in those values into our solution, we get this as our final solution to the problem. Y of t is equal to 2 times e to the 2t minus 3 times e to the negative 4t. One of the really important cases that comes up a lot in physics and engineering is when the roots to the characteristic equation are complex numbers. So let's work through an example that has that. So let's say our differential equation is d squared y dt squared, second derivative of y, plus 9y equals 0. And we're given these two, we're given a couple initial conditions here as well. So the characteristic equation, remember we can write this just by inspection. This term here gives us the second derivative, so that's s squared. And then we have a 9 here by itself. All right, there's no s because this is not a first derivative. So our characteristic equation is s squared plus 9 equals 0. Well, how do we solve for this? S squared is equal to negative 9, right? Well, if we move the 9 over. And so obviously s doesn't have any real value solutions, but that doesn't mean we can't solve this problem. This problem is very solvable. We have to realize that s is equal to plus or minus the square root of minus 9. In other words, s is equal to plus or minus 3j. Remember, j is the square root of -1. So these are complex roots, and they will always be complex conjugates of each other. One is plus 3j, the other is minus 3j. So we can plug in those roots into our solution form, just like we did in the last problem, but now we have that j up there in the exponent. So what do we do with this? Well, one way, probably the best way that I would recommend, is to next invoke Euler's formula and break up these complex exponentials into their corresponding cosine and sine terms. So the first term here becomes cosine of 3t minus j sine of 3t. The second term here becomes cosine of 3t plus j sine of 3t. And then, don't forget about the coefficients a1 and a2 out there. The next thing to do, it's kind of a neat trick here, is just to regroup. Put the cosine terms together here, and then let's put the sine terms together. So the cosine terms, there's an a1 plus a2, right, in front of these cosines. And for the sine, we have a j, and we have an a1 minus a2. In fact, let's see. I've got, okay, so what we're going to do next is we can lump these coefficients together to get, and let's rename them C1, and let's lump all of these coefficients together, including the j, and rename it C2. I realize I think I have a typo here. I think this should be a2 minus a1, but it turns out it doesn't matter because we're going to rename all this junk in front of the sign. We're going to call it C2 anyway. So what we've done now is we simplified our solution to y is equal to C1 times cosine of 3t plus C2 of sine of 3t. And the next thing is we can figure out these two coefficients, C1 and C2, just by using the two initial conditions that we were given up here. So I won't go through the details of that. That's something that you should know how to do. But basically, you just plug these initial conditions in and solve for the coefficient that remains, and you'll find out that C1 ends up being 0 and C2 is 2. So our final solution to this differential equation up here is y of t is equal to 2 times sine of 3t. And so what usually happens whenever we end up with complex roots of the characteristic equation, we always end up with a sine or cosine term, sometimes both, but the solution oscillates. That's the key thing. So now we have enough knowledge to go back and find the solution to our damped spring system that we showed earlier. In fact, it was the first example of this lecture. If you look back, remember we had the spring like this. It's oscillating back and forth on this frictionless plane here, but there was wind resistance or drag. And so, this was the differential equation that we came up with by using Newton's second law. And so now we can go ahead and solve this equation. So the equation is m times second derivative of x plus b times first derivative of x plus kx equals 0. So let's go ahead and look at the solution on the next slide. So here are the 9 steps to find our solution. First one is I just rewrote the differential equation here so we can see it. The next thing we can do immediately is write the characteristic equation. So we have m times s squared, right? We can do this by inspection, plus b times s plus k equals 0. Now we have to solve for s. Well, this is a quadratic equation in s. So we're going to find the roots of our characteristic equation by using the quadratic formula. So s is equal to, remember you take the opposite of b over 2a, where a is equal to m, plus or minus 1 over 2a, again a is the coefficient here, m, and then inside the square root we have b squared minus 4ac, so we have b squared minus 4mk, because m is here and k is there. So this is just standard quadratic formula which you've used since high school. What we can do here is, basically we're going to rewrite these roots before we stick them in our solution. So the first thing I'm going to do is redistribute this 1 over 2m. Let's bring this inside of the square root sign. So in order to do that, I have to square it to bring it inside. So, this 1 over 2m, when I bring it inside, becomes 1 over 4m squared. So I have b squared over 4m squared here, and the 4's cancel the second term, and the m squared, this m gets canceled, and we end up with an m on the bottom. So here's what it looks like after we bring that inside. The next thing we're going to do is there are actually different cases here, but I'm going to assume that this k over m term is larger than this b squared over 4m, okay? And a lot of times it is, not always, but in this, let's solve it for that case because the solution is more interesting. So if this term here is larger than this one, then we end up with a negative value inside here. So this whole term here is going to be imaginary, right? So what I can do, and here's a trick, I can factor out a j and reverse the order of what's inside here. Because remember, a j, when it was inside here, was a -1. So I have k over m minus b over 2m and all squared. I'm rewriting this first term here as a square. So to clean this mess up, this first term here, b over 2m, let's call it sigma. Well, notice here is sigma squared. And then the last thing here, k over m, you'll recognize this, from physics class. This is the natural frequency of this system here squared. All right, if you remember, from a mass on a spring, the frequency omega is given by the square root of k over m. So k over m is the square of the natural frequency omega naught. So we can rewrite our s as negative sigma plus or minus j times the root of the natural frequency squared minus sigma squared. And it turns out that all of this stuff here, the square root term with all that stuff inside of it, is going to end up physically being the frequency of oscillation of this thing when it goes back and forth. So using that, kind of like looking ahead, I'm going to rename all of this stuff here as omega. All right, now this omega is not the same as omega naught. It's a little bit different because it's subtracted from by sigma squared. So anyway, our roots of our characteristic equation can now be written very simply and compactly as negative sigma plus or minus j omega. So the next thing is to take these values here, it's negative sigma plus j omega and negative sigma minus j omega, and plug them into our solution form here. And that's done here, and you can see I've sort of split apart, I distributed the exponent here and factored out an e to the minus sigma t. This is all just, algebra now, what we're doing here. And once I get it in this form here, I'm going to use Euler's formula to write these complex exponentials out as cosines and sines using Euler's formula here, okay? The next thing to do is to regroup. So let's put the sine terms, these two guys, put them together. This is just like the last problem we did. And then the cosines are grouped together, and then we can group the sine terms over here. And then let's rename these constants, C1 and C2, let's rename that K1. And let's rename all this junk here K2. So our solution is looking a little simpler now. Our solution looks like e to the minus sigma t times quantity K1 cosine omega t plus K2 sine omega t. The last step here is to apply our initial conditions. The mass at time 0 is over here at A. So x of 0 is equal to A, and you can see when you plug in t equals 0 into this equation here, you end up with A must equal K1. And the other initial condition is it starts from rest because we let it go right here at time 0. So the initial velocity is equal to 0. And when you plug that in, you'll have to take some derivatives here because velocity is the derivative of position. But when you do that, you'll find out that K2 has to be equal to 0. All right, so I know I kind of went over those steps pretty quickly, but I'm hoping that's something that you've done in the past, how to apply initial conditions to find those coefficients. Our final solution then, with K1 is equal to A, the amplitude, and K2 is equal to 0, comes down to something, a very simple looking form. X of t, the position of this mass, is given by the following equation. A, which is the amplitude right here, times e to the minus sigma t times cosine of omega t. Now, what is sigma? Well, you have to go back up here and remember that sigma is b over 2m. So that depends on, what the coefficient was of drag, and it depends on what the mass is of this block here. And omega is the frequency that it vibrates or oscillates back and forth. Omega is given by omega naught squared minus sigma squared. Okay, and those terms are all shown in here. So what this thing is doing is basically a damped oscillation. We talked about this earlier in this lecture. It's oscillating with frequency omega, but its oscillations are exponentially decaying due to the damping. All right, the next step is how to solve non-homogeneous linear differential equations. So what do we mean by a homogeneous versus non-homogeneous differential equations? Well, remember, for homogeneous equations, the right side of the equation is 0. Here's an example here. We have all the derivatives and of y, and we have y itself. Put all the y's over here on the left. Whatever is left on the right determines whether or not the equation is homogeneous or not. So this one is homogeneous. A non-homogeneous or inhomogeneous differential equation, when we move all the y's to the left side, we end up with some x's over here on the right. And this makes it a whole different creature to solve. This x is the input of the system. All right, you think about our standard system notation here. We have the system with x going in and y going out. Well, all the differential equations we just looked at, up until this point in the lecture, they all had no input over here. The system was just sort of put in motion and let go, and we're finding the output. But now the system is being driven by something over here, and this x. So x is sometimes called a driving function, or a forcing function, or a source function. So how do we solve an inhomogeneous differential equation? Well, the good news is it starts out very similar to, in fact, exactly similar to the way we solve the homogeneous differential equation. So, if we start with this equation here, so notice, over here on the right, we don't have a 0, okay? But that's okay. We're going to start by finding the characteristic equation of the homogeneous equation. So all we have to do is ignore all this stuff over here, whatever's over on the right, and just set it to 0. So this is exactly what we did in the first part of this lecture. So, based on if the equation looks like this here, we end up by inspection, we have s squared plus a times s plus b equals 0. So there's our characteristic equation, and then we would solve the roots here, by either factoring or quadratic formula or however we need to do it. And those roots will give us the homogeneous solution. So here, y, notice the little h here to remind us that this is not our final answer, but this is part of our answer. Part of the solution here is the homogeneous solution. So, as always, it's some constant times e to the s1t, where s1 is one of the roots, plus a2 times e to the s2t, where s2 is the other root, and a1 and a2 are just some constants that we're going to have to find later. All right, so the other half of this solution is to find what's called the particular solution, y sub p, and that depends on the form of whatever is over here on the right side. So this table here is a handy table to use for finding the form of the particular solution. So, for example, and by the way, I should just clarify here, this table is valid for cases where the roots here are non-zero, okay? There are some other, tricks to use when the roots are 0. But for what we're going to do in this class, I think we'll always encounter non-zero roots to our characteristic equation, so we can use this table. So what this says is that if on the right side of the equation we have a constant, then our particular solution will be just some constant. If the non-inhomogeneous part over here, x of t, is equal to an exponential function like this, then the particular solution will also be exponential. All right. Now, what if the driving function over here on the right is equal to a sine or a cosine. Well, what we have to do is the particular solution must include both. So notice if we have a sine here, we have a sine plus a cosine, and they each have their own coefficients. Likewise, if we just have a cosine over here, we still have to use both sine and cosine here. All right, and there's another one that uses, in the case where the driving function or the input over here is a polynomial or part of a polynomial, some power of time, for example, then we have to use this form here, which I don't think we're going to encounter in the examples that I use. But the key thing here is once we write our particular solution using this table, we have to plug it back into our equation up here and solve for these constants, however many we have in our particular solution. And then once we do that, we're going to add our homogeneous solution, which was this guy, plus the particular solution, which we did in these steps, add them together, and finally, if there are initial conditions, we'll have to apply those to figure out any of the remaining constants. Okay, so this process obviously is a little bit more involved than what we saw up till now. So let's look at some examples. So here's our first example. It looks like I probably didn't solve this all the way through, but at least I'll show you how to set this one up, and then we'll see some more examples that follow. This was our differential equation for the LRC circuit that we actually found before. And the key thing that we're looking at here is, all the y's are on the left side, and the x term is on the right. This x term, represents the input to this system. It was probably some input voltage or something like that. So this is obviously a non-homogeneous equation because this is not zero over here. So, to solve this, we start by finding the characteristic equation. And remember, all we have to do is set the right side equal to 0. And then by inspection, I can write the characteristic equation as s squared plus r over L times s, first derivative, plus 1 over LC equals 0. And so that's what's shown here in the box. And then, depending on what the values of R, L, and C are, we could use the quadratic formula to find the roots of this equation here, which would be S1 and S2, and we can put those into our homogeneous solution here, y sub h. Now, to find the particular solution, we have to look up here and see what's on the right side of this equation. Now, in this example, we're not given what x is. So, if x was just a constant voltage or something, then we're going to use this form here. If x was, let's say, a cosine function, all right, so we hook this up to a signal generator, and so this thing is oscillating back and forth, then we're going to have to, x of t would be this cosine here, and for our particular solution, we would have to use this form here. But since I have, this problem, we're not really going to work this one through, obviously, because I didn't specify what x is. We really can't go any further, but let's move on to the next example where it'll be a little more specific on how to solve this. Okay, so in this example, we have a first order non-homogeneous linear differential equation. So dy dt plus 3y equals 5x, where x is equal e to the minus 4t times the step function ut. All right, and we're given that this is a causal system and it's initially at rest, so this is our initial condition that y of t is equal to 0 if t is less than or equal to 0. So to solve this thing, our goal here is to figure out what is y, what is the output of this system for this input given over here. So what we're going to do here is find the homogeneous equation first. So we let the right side equal 0. So we have dy dt plus 3y equals 0, and the characteristic equation, I'm going to skip this step and I'm going to do it by inspection. That's the short method, right? This is a first derivative of y, so that's going to give me s, and here we have 3y, which is going to give me 3. So I have s plus 3 equals 0, or s equals -3. So we have just a single root because it's a first order equation. So my homogeneous solution, y sub h, is equal to a times e to the minus 3t. That minus 3 came from the root right here. We don't know what a is yet. The particular solution, now notice the x function over here on the right side, x, is an exponential function, e to the minus 4t times ut. So our particular solution form is going to have the same exponent, but I'm going to use a different constant here. So it's going to be c times e to the minus 4t times ut. And so what I need to do next is take this particular solution, y sub p, and plug it back into my original equation here, the whole thing. All right. So when I do that, I'm going to get, so what I have to do is take the derivative. This is the derivative of y sub p. So I'm going to have minus 4, that comes out in the front, minus 4c times e to the minus 4t, plus 3 times y particular. All right. And again, y particular is this right here. So I have 3 times c times e to the minus 4t equals, now remember the right side here is 5x, and we use this for x. So it's equal to 5 times e to the minus 4t. So notice that this thing, you know, it's a little messy looking, but it cleans up very nicely because each term has e to the minus 4t in it. So I can immediately cancel all of those. And I end up with minus 4c plus 3c equals 5. Well, that's easy to solve for. That's c equals a -5. So therefore, my particular solution is minus 5 times e to the negative 4t times the step function. So the total solution then to this problem is the sum of the homogeneous solution plus the particular solution. So here's the homogeneous solution. We add to that the particular solution right here. And the last thing we have to do is figure out what is a right here. Well, we get a from the initial condition. Y at time 0 is equal to 0. That was given to us. And that, you know, becomes this equation right here becomes a minus 5 when t is equal to 0. Therefore, a is equal to 5. So with a is equal to 5, we can finally have for our final solution y of t is equal to 5. That 5 is on both terms, so I factored it out. E to the minus 3t minus e to the minus 4t. Here's another example of a non-homogeneous linear differential equation. So we're given second derivative of y plus 2 times the derivative of y minus 8y equals 3x, and this time x is equal to t times the step function, and we're given this initial condition. So I won't go through this you know, in great detail, but I have put the detailed steps here with everything you need to know to solve this. So it's probably good to do this on your own and see if you can follow the steps. But basically, we're finding the homogeneous solution first, and you know, by inspection, I can just look at this equation and write s squared plus 2s minus 8 equals 0. So that's the characteristic equation. That's simple to do. And you know, notice it factors, and so we can solve the roots of the characteristic equation are s equal minus 4 and s equal 2, giving us this homogeneous solution. Now, the particular solution, we have to look at the form of x, and it's t. All right, so we go back to that table, and we find that the particular solution form has to be c1t plus c2. So plugging that back into the original equation, we end up with this right here. We end up with this equation for c1 for our constants and as a function of time. And we can solve this for c2, all right, and stick this back into our particular solution. And we get a particular solution that looks like this. So the total solution then, and again, I apologize, I know I'm going through this pretty quickly, but you should be able to trace through these steps and do them on your own. They're not that difficult. It's just algebra at this point. We're just adding our two homogeneous and particular solutions together to get this expression here, and then finally applying the initial condition and putting that into our final form like this. So it looks like our final form here, we end up with two constants that we don't know. The reason for that is we were only given one initial condition. And our last example here is another second order linear differential equation that is non-homogeneous. This case, well, here we have the second derivative of y plus 2 times first derivative of y plus 5y is equal to x, and x is equal to a cosine function, cosine of 3t. And this problem, we're asked to find the steady state solution. In other words, what does this system do when time goes very long into the future, when time goes to infinity? All right, that's the so-called steady state solution. So as always, we're going to find the homogeneous solution first. So we can write the characteristic equation. Again, you don't have to do all these steps, just write it by inspection. S squared plus 2s plus 5 equals 0. So that's right there. And you can solve this, it turns out that the roots are complex, all right? So when you use the quadratic formula, you're going to end up with -1 plus or minus 2j. I put those two solutions here into the exponential form and factor out the e to the minus t term, bring it out in front, and it looks like this. And then finally, I can use Euler's formula to write these exponential complex exponentials in terms of cosines and sines, regroup, put all the cosine terms together, all the sine terms together. We've done this, a couple times now in different examples, so I don't need to go over that in detail, I don't think. And then we can rename these constants. The a plus b here I call lowercase a, and j, a minus b over here, I call lowercase b. This is what our solution now looks like. Okay, now one thing we see here is that this homogeneous solution are both terms here are decaying exponential functions. So normally, we would include these in our solution, but remember we were told to find, we don't care what this system does in the short term. We want to know what does it do in the long term, in the steady state. So if we plug t equals 0, then both of these terms vanish. So this is kind of good, actually. Our homogeneous solution is just 0. There is no homogeneous solution. All we need is the particular solution. So that's what we're going to do next and last. Okay, so the particular solution form, remember we had the input of this system was a cosine function, a cosine of 3t. So the particular solution from that table a few slides back is C1 sine of 3t plus C2 cosine of 3t. Remember, we have to include both a sine and a cosine term. So we have to take this solution here, this particular solution, and plug it back into the whole differential equation, the left side and the right side. And when we do that, and we have to take this is a little bit messy here because you have to take a couple derivatives of this, and you have to take the first derivative of this and plug it all in, so you end up with lots of terms here. Okay, so this would be a good exercise to make sure that you can get this same result. The final thing to do is group all the cosines together on one side, and what I did was group all the sines together on the other side. And one of the math tricks here is that a cosine and a sine, those are independent functions. In order for this side to be equal to this side over here, both sides must be 0. All right, now that's only going to happen when whatever is in these brackets is equal to 0. So what happens here is by setting this equation equal to 0 and this equation equal to 0, we end up with two equations and two unknowns which can be solved, and here are the answers right here. Obviously, I'm not showing the details here. This is just some tedious algebra to solve for two equations and two unknowns. But finally, I can plug, once I know C1 and C2, I can plug them back into my solutions up here, and I get this right here. And so this is what our final solution to this thing looks like. This example, by the way, is an example of what's called forced oscillations. And this can happen with a mass on a spring, or it can happen with an LCR circuit that's connected to, say, a signal generator that drives the circuit. So you can see that the frequency of oscillation of both the sine term and the cosine term is 3. And that's the same frequency that was given in the beginning of the problem as the input of this system. So that makes sense, is that the system is going to oscillate at the same frequency that it was driven at. So that was a rather long part of this lecture. I realize, this one, but again, we had to, I wanted to show you quite a few different examples, and hopefully, differential equations is something you're already familiar with, or maybe this is, if you've had it before, this is a good review for you. If you haven't had Diff-EQ, obviously, this has been, your eyes are probably spinning right now after seeing all this in one lecture, because basically I've just covered several weeks of a math class in the last hour, but we're going to require the use of these differential equations to analyze systems in this course. So that's it for this part of the lecture. I will see you shortly for part 5 next. Goodbye.